Hello, I am Ali Izzad Kasti. Today, in this detailed and comprehensive tutorial, we are going to discuss and thoroughly explain the process of synchronizing two LS inverters by utilizing their analog inputs and outputs. Our first inverter, which we will be working with, is the H100 model, and the second inverter that we will use in this setup is the G100 model. In addition to these two inverters, we have also incorporated an LS compact PLC, specifically the model XEC-DR32H, and we have connected this PLC to an analog input card, which is the model XBF-AD04A. Furthermore, we have included a weight indicator in our system, which is the model SI580E from the SUA brand, and this weight indicator is connected to a single point load cell, model AB 125 kilograms. What we aim to achieve in this setup is to use the 0 to 10 volt analog voltage output that comes from this indicator, and at the same time we want to connect this output simultaneously to both the analog input of the inverter and the analog input of the PLC expansion card. This means that we have taken the positive and negative analog outputs from the indicator and connected them to the analog input of the drive, which are labeled as V1 and CM, and we have also connected them to the analog input channel 0 of our XBF-AD04 card. Since the analog output of this device is voltage based, these two analog inputs are, in effect, connected in parallel, and this parallel connection does not cause any issues or problems for us in the operation of the system. The important point to note here is that we must use the voltage analog output and not the current output, so that we can safely and effectively parallel these two connections without any risk of interference or malfunction. Next, what we did in our setup was to use the analog output of our drive, specifically from the terminals labeled A01 and CM, which are the analog output terminals of this drive, and we connected these terminals to the analog input of our second drive. The reason for doing this is so that we can synchronize these two drives with each other through their analog inputs and outputs, ensuring that they operate in harmony and coordination. Okay, what we have accomplished here is a method that is commonly used in filling machines in various industries. In fact, with the help of the equipment that I have introduced and described, we have designed and implemented a two-stage filling machine that is capable of measuring the weight using this indicator and carrying out the filling process in two distinct stages. The program that we wrote and implemented in the PLC operates as follows. When the weight indicator shows 0, which means there is no load present on the load cell, the frequency of both inverters should be set to 50 Hz. In this initial state, when we press the start button, both the first and second inverters start up simultaneously and enter the circuit in perfect synchronization with each other. When the weight measured by the indicator reaches 3 kilograms, the second inverter should stop its operation and exit the circuit. And when the weight reaches the target value of 5 kilograms, the first inverter should also stop, its frequency should drop to 0, and it should exit the circuit as well. So, in a sense, we are performing this 5 kilogram filling process in two separate stages. Now, let's proceed to test this setup. I will press the start button here. As you can see, both inverters start running at the same time and enter the circuit in perfect synchronization. Now, when I place a 3 kilogram weight on the load cell, the second inverter should exit the circuit and its frequency should drop to 0. Let's observe what happens next. Okay, the weight reached 3 kilograms, and at this point the frequency of my second inverter dropped all the way down to 0, and it exited the circuit. Now my first drive is operating at a lower frequency and continues the filling process until the weight reaches 5 kilograms, which is the target value we set. When the weight reaches 5 kilograms, you'll see that the frequency of my first inverter also drops to 0. It exits the circuit and our filling process is complete. Next, we'll get more familiar with the PLC programming and the wiring we did. As mentioned earlier, we connected the voltage analog output of the indicator simultaneously to both the first drive and our analog input card. The important point to note here was that since these two are effectively in parallel, the analog signal we use must be voltage based. The next thing we did was connect the two inverters together via their analog input and output. That is, we connected the analog output of the first inverter to the analog input of the second inverter, and we did this using a current analog signal, specifically the 4 to 20 milliamp analog. Here, we used the 4 to 20 milliamp analog for communication between the two drives. Now, each of these devices requires a set of configurations, which we'll get to next. First, the settings for the H100 inverter. We set parameter DRV07 to V1. DRV07 is related to frequency, meaning in this mode, the frequency is received through the voltage analog input of this drive. DRV06 is related to run and stop of this drive, which can be controlled via digital inputs. We used P1 and CM, so we set DRV06 to FXRX1. We set out 01 to frequency, which means that the analog output here is based on frequency. Out 02 is a gain parameter, and we need to carefully adjust this gain so that our two drives are frequency synchronized with each other. We set this gain parameter to the value of 77.8, ensuring precise synchronization between the two drives. This careful adjustment is important for maintaining stable and reliable operation. There is a DIP switch, which stands for Dual Inline Package Switch, located on the HSD drive itself, and in our setup we have set switch number 5 to the AO position. As we mentioned earlier, we connected the HSD drive and the GSD drive to each other via analog current, so we set this to AO to enable analog output. In fact, the analog output that this drive provides is in current form, meaning it is specifically 4 to 20 milliamps, which is a standard range for industrial analog signals. We set input in 08 to 0, in 09 to 100, in 10 to 10, and in 11 to 0. These settings you see here are related to the fact that the frequency this drive receives works like this. When our analog input is at 0 volts, the frequency is at its maximum value. And when our analog input is at 10 volts, the frequency is at 0. In fact, it works in reverse. So in the parameters, we need to set the frequency on the drive in this way. This configuration ensures that the drive responds correctly to the analog input signal, allowing for precise control over the frequency output based on the input voltage. Alright, the next setting is related to the G100 drive. On the G100 drive, we set FRQ to 5, which means that the frequency is received through the analog current input. We set DRV to 1, which is related to the run/stop function and is controlled via the P1 and CM terminals. We set input IN53 to 4, IN54 to 100, IN55 to 20, and IN56 to 3. These settings are also related to the frequency of this drive, and again it is set to work in reverse. That is, when our analog input is at 4 milliamps, the frequency is at 50 Hz, and when our analog input is at 20 milliamps, the frequency drops to 0. As we mentioned, in filling machines, the inverter must definitely be set up this way. The next group of settings that we are going to discuss are specifically related to the SIP580E display unit. On the SIP580E, as we previously mentioned, we have decided that we want to utilize its analog voltage output feature, so it is necessary for us to set parameter HF13 to a value of 1, HF14 to a value of 0, and HF15 to a value of 10. Say, HF13 is the parameter responsible for configuring the analog output so that it operates in voltage mode rather than in current mode. HF14 along with HF15 are the parameters that together determine and define the analog output range for us, which in this particular case is set from 0 volts all the way up to 10 volts. Later on, as we continue, we will become more familiar with the process of setting and adjusting these hidden functions, and we will gain a deeper understanding of how to work with them effectively. So in order to set the analog output of the SI580E weight display to voltage mode, meaning from 0 to 10 volts, first, when the weight display is turned off, go to the back of the device. To begin, you will need to carefully unscrew these screws that are located in this specific area, and then gently remove this protective cover from the display unit. Now, as you can clearly see here, there are actually two separate boards situated inside this display enclosure. The upper board, which is designed to slide out smoothly, needs to be carefully removed from the display for the next step. When you take a closer look at this upper board, you'll notice that there is a DIP switch located right here, which by default is set to operate in current mode. We need to change this setting by switching it to voltage mode instead. And you will also find that this particular section is clearly labeled on the board itself for your reference. Please make sure to handle all components gently and double check the switch position before proceeding to the next step. It says 10 volts, which means we need to set it to voltage mode and then reconnect it to our display. Like this, I'll connect it back to the SI580E display. This is very easy to do, and then we can put the cover back in its place again. Now, another adjustment that we need to make, as I have explained to you before, is that we have to enter the hidden functions of this display unit. To access these hidden functions, we need to press and hold the F button for a few seconds, making sure to keep it pressed steadily. At this point, the display will prompt us by asking for a password. In response, we press the till button 4 times in a row, one after the other, and then we press the F button again. Now, if we press the hold button, we will enter the hidden functions of the display. As I mentioned earlier, the first setting that we need to adjust is called HF13. We enter HF13, press the F button, and this should be set to the value of 1. When we press the F button, it saves the setting. Next, we go to HF14, press the F button, and this value should be set to 0. Then we go to HF15, and this should be set to 10. We press the F button and it saves. If we press the button below, we exit the settings, all right? Now, what we want to do and what we are aiming to accomplish in this particular step is to carefully review in detail the analog wiring for this project that we're currently discussing together as a group. Here in this diagram, we have the H100 inverter, which is a crucial component, and we're specifically looking at its control terminals, which are essential for proper operation. In addition to that, we also have the G100 drive, and these are its related control terminals, which play an important role in the system. This right here is actually the back of the SIE580E display, which is used for monitoring and control, and this is our PLC, or Programmable Logic Controller, along with its expansion card, which allows for additional input and output capabilities. Alright, so first of all, what we do is take a wire from the positive analog output of our display and we connect it to the V1 terminal on the H100 inverter, ensuring a secure and proper connection. Also, from the negative analog output of our display, we take another wire and connect it to the CM terminal on the H100 drive, making sure the polarity is correct. Next, again from the positive analog output, we take another wire and connect it to channel 0 of the analog input card.
specifically to its positive terminal to ensure the signal is properly received. Similarly, from the negative analog output of our display, we take another wire and connect it to the negative terminal of the analog input channel 0 on our expansion analog card, maintaining the correct wiring configuration. As we mentioned earlier, these two connections are actually made in parallel, which means that both devices receive the same analog signal at the same time, allowing for synchronized operation and accurate data transmission throughout the system.
And from there, at that point, from the analog output of our H100 drive, we take a signal and connect it to the analog input, labeled as I2 of our G100 drive. As we mentioned earlier, we are connecting these two inverters together via analog current, which allows them to work in coordination. We are linking these two drives together through an analog current connection. Also, from the CM terminal of the H100 drive, we connect it to the CM terminal of the G100 drive, establishing a common ground reference. In fact, these two drives are connected to each other via analog wiring. This part is related to the analog output of the H100 drive, and this part is related to the analog input of the G100 drive. Now, the next wiring we will review together is related to the run and stop of the two inverters. As we explained earlier, the run and stop of these two drives are controlled by the program we write in the PLC, or programmable logic controller. So we take a wire from the COM0 terminal of our PLC and connect it to the CM of our G100 drive. Also from Q1 of our PLC, we take another wire and connect it to P1 of the G100 drive. Then from the CM of the H100 drive, which is our first drive, we take a wire and connect it to COM0 of the PLC. And from the P1 terminal of the H100 drive, we take a wire and connect it to the Q2 output of the LS PLC. So this is basically how the wiring is done between the PLC and the two inverters for the run and stop functions of these inverters. All right, the next important topic that we need to discuss is about scaling these analog inputs. As we explained earlier, we want to write a program in the PLC so that when the weight reaches 3 kilograms, one PLC output is activated, and when the weight reaches 5 kilograms, another PLC output is activated. We connect the weight to the PLC via the analog input, meaning we connect the weight display to the PLC's analog card. In previous lessons, we explained that if the analog input card is 12-bit, the analog input it receives is converted in the PLC to a value between 0 and 4000. So, when our weight changes between 0 and 5 kilograms, in the PLC we have a value between 0 and 4000. Now we need to scale this. That is, when our weight reaches 3 kilograms, we need to know what value between 0 and 4000 that corresponds to. In mathematics, we know that if we have 2 points, x1 and x2, and y1 and y2, and if these 2 points are defined, we can find the linear equation between them. We can imagine it like this. Our x1 and x2 are actually the 0 to 5 kilograms of the load cell, and our y1 and y2 are the 0 to 4000 that the analog card gives us. We can find the linear equation that passes through these 2 points. The equation is y equals ax plus b, where a is the slope, which we calculate using the formula, open parenthesis, y2 minus y1 close parenthesis, divided by open parenthesis, x2 minus x1 close parenthesis. So we can find the linear equation between these 2 points, and based on that, for any load cell capacity, we can determine the corresponding value between 0 and 4000. We have implemented this in programming, and we will review it together in the next steps. Now let's enter the XG5000 software environment and do the programming together. We have entered the XG5000 software. First, we go to the I/O parameter section. In the I/O parameter section in the very first row, we click here. In this part, we need to select the PLC model. Our PLC is XEC-DR32H, so we select it here. In the next row, we define our analog input card. We click here, then in the special module list, I click the plus sign. It brings up the list of cards for us. I select the analog input XBF-AD04A. I click on it, and if I click here, a window opens for us. In this section, I enable channel 0. And for the input, I set the input range to 0 to 10 volts. For the output type, I set it to a value between 0 and 4000. I click OK, then I click Apply here, check the All box, and finally I click OK again. So, as I explained to you earlier, and as I have previously mentioned in our discussion, I mentioned that I wrote a function which I have named scale, and this is a function that I can conveniently call from the functions and function blocks section of the programming environment. Whenever I need to perform a scaling operation, or whenever the need arises in my project, I can use this function without any difficulty. This function, which I have carefully designed, has several important parameters: x1, x2, y1, y2, an analog input, and a scale analog. As I explained before, I set x1 to 0, x2 to 5, y1 to 0, and y2 to 4000. In this part of the process, I set channel 0 data, which is specifically related to the analog input card. That is, the data that I am reading from the analog input card is directed here. And I name the output scale analog for clarity. The output that this function provides us is in real format, and these inputs are also received in real format, and the output is also in real format, ensuring consistency in data types. Now, inside this function, we have written a program, and through this section, if we want, we can access the program that has been written inside here, which is basically the linear equation I explained to you earlier, y2 minus y1, x2 minus x1, and here we calculated the slope, and the rest of the steps are related to obtaining a linear equation. So we derive the linear equation here, and through this we obtain the b or the y-intercept. And finally, after completing all these steps, we have a fully functional scaling function that can be used whenever necessary in our project. This approach ensures that the scaling is accurate, reliable, and easy to implement, and it allows for flexibility in handling different ranges of input and output values, which is essential in many automation and control applications. If you have any questions about how this function works or how to use it in your own projects, please feel free to ask, and I will be happy to explain further or provide additional examples as needed. That scale analog, which is given to us as the output, is essentially the program for obtaining a linear equation. Since this is a practical program, we turned it into a function, and we can save it on our laptop for future use. Whenever we want, we can use it in programming, and the function I created is called scale analog. If I press the F10 key on my laptop, it will show up in the section related to functions and function blocks, and I can call it whenever I want. In the next lessons, I will teach you step by step how you can turn a program into a function so that you can reuse your code more efficiently and make your programming tasks easier. As we mentioned, our scale analog section is in real format. Here, I used a conversion from real to integer, so the scale value it gives us is converted, and I named it weight, which actually gives us the weight. Here, it receives a value between 3 to 4,000, and its equivalent is the weight that is given to us here. Now, we want to use this weight value in our programming. Here, I used a normally open contact, named it start, and assigned it the address IX0.0.0. At the same time, I used two set coils, one for running our first inverter and another for running our second inverter. I gave the first one the address QX0.0.1 and the second one QX0.0.2. Now let's do the comparison. We said that we used a GE or greater than or equal to here. I set input 1 as weight and input 2 as the value 3 kilograms. We said that if our weight is greater than or equal to 3 kilograms, our second inverter should turn off, meaning it should be reset. If the weight becomes greater than or equal to 5 kilograms, our first inverter should be taken out of the circuit and reset.